Hi, this is Mr. Anderson, and today I'm going to be talking about speed, velocity, and acceleration. If you've ever seen Usain Bolt run from Jamaica, well, first of all, it's highly impressive, but you have an understanding of how fast really is. In physics, we deal with really just two of these. In other words, speed is a scalar quantity. And you've used speed your whole life. You say, my car can go 20 miles an hour, or my car can go 200 miles an hour, and we're talking about speed. It's a scalar quantity, and if you don't really know what a scalar quantity is, make sure you watch the video on that. But velocity and acceleration are vector quantities, and so they include not only the magnitude, but also the direction at which velocity or position might be changing over time. And so in this video I'm going to show you how to do some simple problems with velocity and acceleration, kind of explain what it is, but we'll get into a lot more detail when we look through position versus time and velocity versus time graphs eventually. So let's get going. Before I get started, however, there is a little cheat that I want to remind you, and that's because I live in the U.S., and since I live in the U.S., I really have a hard time dealing, just in my brain, with meters per second. And so if you do any problem in physics, you always have to use the units meters per second, but in the back of my head I have this. In other words, if I say something's going 10 meters per second, in the back of my brain I have to think, oh, that's about 22 miles an hour. Because that gives me an idea of really how fast something is going. So if you want to use that in the back of your head, you can. But don't use it in your equations, or you're going to get the wrong answer. Now, velocity is a vector, and what does that mean? When you're ever talking about velocity, you have to say not only, let's say, 2.6 meters per second, but you have to give me the direction that that's moving in. So it could be north, or it could be west, or it could be up, or it could be down. And so if you ever give a velocity, make sure you have the direction. Now you're going to find immediately in this video that I quit talking about direction. And so you may think, he just told me direction's important, but now he doesn't even use direction. And the reason why is that we generally use a coordinate system like this. And so if an object is moving up, we'll say, then it's going to have a positive velocity, and so that positive actually tells me the direction it's moving in. Or if it's not sitting on something and gravity pulls it down, then it's going to move in the negative direction. Or in the problems today, Usain Bolt, I'm going to assume, is starting at the origin, and then he's running in the positive direction. But if the wind came up, a real big wind, and blew him in the opposite direction, then he'd be moving in the negative. And so I'm not cheating, I'm actually including positive and negatives to explain that. Also, that you should understand the difference between an average and an instantaneous velocity. An average velocity is looking at a certain period of time and saying how fast did it move during that period of time. But along that race of Usain Bolt, he has all these different instantaneous velocities that are a little bit different. And the best way to explain that is maybe with some videos that I just shot. So let me bring up one of these. This is a video of me. Let's see, go back to the beginning. So this is me taking a weight and then just dropping the weight, like that. So what I can do, let me go back for just a second. If I go right here, and I think I should be able to draw on this. So what I can do is I can actually mark where that weight is. So let's go back a second. So right here, the bottom of the weight, we'll say, is right there. And now it drops a frame, and the bottom of the weight is right there. And it drops a frame, and the bottom of the weight is right there. And now it's right there. And now it's way down here. And so what we can look at is that this is an object that is changing in velocity. And so its velocity way up here was actually 0, and then its velocity changed, and it got faster and faster in the negative direction over time. And so that would be an instantaneous velocity wherever it is. But I could also take this whole thing and figure out what's the average velocity over that. And so make sure you kind of understand the difference between the two. Let's try another one of these. Here's another video I just made. So this is just an object that's rolling across the table. So let's get that back again. So I'm going to give it an initial push, like that. So I give it an initial push, and then according to Newton's laws, an object in motion tends to stay in motion. And so I'm going to mark the middle of the object right here. It's going a little slower, and so let's go a couple, 1, 2, 3 frames, and now it's right here, 1, 2, 3 frames, and now it's right here, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. Okay. And so I gave that an initial velocity, and if you look at it, it seems to be uniform. And so in this case, we'd actually have an instantaneous velocity at any one point that's actually equal to this average velocity over the whole distance. And when we get to doing some graphing, that'll make a little bit more sense. But remember, there's a difference between the two, and so I kind of will use them interchangeably, but make sure you understand which of the ones I'm talking about. Okay, so definition time. If you need to solve some problems, this is the definition for velocity. So definition of velocity, it's simply change in x over the change in t, where x is its position and t is equal to the time. And so to solve a problem that you might have like on a worksheet or a test, let's do Usain Bolt. So his world record in the 100-point meter dash is 9.58 seconds. And so to figure out his velocity, this is how it works in my brain. I go delta x over delta t. So delta x is simply the change in x over the change in t. And so how far does his distance change? Well, it's going to be 100 meters. Always make sure you're including the correct number of significant digits and the units as well, otherwise you're going to get stupid answers. Now we look at the change in time. Well, the change in time is 9.58 seconds. Okay, so how do we do this? We're going to divide 100 meters divided by 9.58 seconds. I did that just a second ago, and I got 10.4. And the units then are going to be in meters per second. And so the average velocity of Usain Bolt during his whole run is 10.4 meters per second. Using that brain trick again, if I take that times 2.2, he's going roughly 23 miles per hour to give you an idea of what his average speed is. And so that'd be a pretty simple velocity kind of problem. Sometimes it doesn't start from rest. In other words, it doesn't start from a time being 0 and a velocity being 0 as well. And so a better way to remember what velocity is instead of the change in x over the change in t is it's the final x, or its final position, minus its initial. And so get used to this in science. The F always stands for final and the I always stands for initial, divided by the final time minus the initial time. And so this is a better way to explain what velocity is. And let's try a problem where it actually varies a little bit. These are the splits from the Usain Bolt's race. This is actually in the Olympic record where he ran 9.69. And so the first thing let's do is let's try to figure out the velocity for the first 10 meters. And so velocity, remember, is going to be xf minus xi, where xf is the final position, and then it's going to be tf minus ti. Okay. And when you ever solve problems, you want to make sure you identify, what do I know? Well, what's the final position? That's going to be 10.0, so 10.0. What was his initial position? And again, I should put meters. What was his initial position? That was 0, so that's minus 0. What was his final time? That'd be 1.85. 1.85. And then what was the initial in seconds? It's 0 seconds. So what I get here is, well, roughly 10.0 meters over 1.85 seconds. And so when I worked this earlier, and I get 5.41. So it'd be 5.41 meters per second. Now, why does this have 3 significant digits? Because that has 3 and that has 3 as well. So how fast is that in miles per hour? It's not very fast. I don't know, like 13, 14 miles an hour? Let's look how fast he's running later in the race, though. And let's try it way down here. So if we go way down here, let's say at this point. So remember, velocity is going to be final x minus initial x over time final minus time initial. And this is why you'll start to see why it's important that we kind of keep track of that. So during this next 10 meters, he ends up at 70.0 meters, and he started at 60.0 meters. So this would be the initial distance. The final time is 7.14 seconds, and the initial time is 6.32 seconds. So what does that equal? Well, that equals 10.0 meters divided by 0.82 seconds. And so the right answer should be 12.2 meters per second. So that'd be the right answer with 3 significant digits. Doing that into miles per hour, it's around 27 miles an hour, so it's a ridiculous amount of speed. And so this would be his speed down here, 12.2 meters per second. And remember when we were way up here, his speed was only 5.4 meters per second. And so what has happened from here to here? Well, the velocity is actually increased. And so you know what that means. What does it mean when your velocity is increasing? That means that we're accelerating. And so not only is the velocity important, but what happens to the velocity over time is also important. And so that's what acceleration is. Acceleration is the change in velocity over the change in time. And if you'll look, the equation is very similar. We take the final velocity minus the initial, and then divide that by the final time divided by the initial time. Now the units are a little bit weird if you think about it. We're taking meters per second, which is what the velocity is measured in, and we're dividing it by a second. And so lots of times we'll just write that as meters per second squared. Now what's one acceleration that you should learn? This is the acceleration due to gravity. So the acceleration due to gravity is negative 9.8 meters per second squared. What does that mean? If we take a person like this standing at the top of a cliff, and they fall off. At 0 seconds, they're going to be going 9.8 meters per second. Excuse me. At the top, they're going to be going 0 meters per second. But after 1 second, they're going to be going 9.8 meters per second. So if you jump off a cliff, after 1 second, you're roughly going 23 miles an hour. After 2 seconds, you're going 46 miles an hour. After 3 seconds, you're going, 68, whatever, miles per hour. And so you're going to go really, really fast, very quickly. And so that's acceleration due to gravity. Why it's in the negative is that, remember, on our coordinate system, this would be in the positive, and so this is going to be in the negative as we go down. Let's try an actual problem to how you would have to solve a problem like this. This is the Bugatti Veyron, which is made by Volkswagen, and it's the fastest production car that you could buy, which if you had a bunch of money, goes like 250 miles an hour. And so let's try to do an acceleration problem. So acceleration, remember, is the change in velocity over the change in time. So let's figure out if it can go from 0 to 60 in 2.46 seconds, what kind of an acceleration are we talking about? So again, that's going to be VF minus VI over TF minus TI. So what's our final velocity? Our final velocity is going to be 60 miles an hour, which we couldn't use in an equation. We have to convert that to meters per second. So that'd be 26.9 meters per second minus 0, because it starts at a standstill. What is its final time? Its final time is going to be 2.46 seconds minus 0 seconds, because it goes from a standstill. And so now we could figure out the acceleration. So 26.9 divided by 2.46 is going to be 10.9 meters per second squared. So that'd be the right answer. So going back, again, figuring out what the acceleration due to gravity is. If you're falling off a cliff, you're going to experience an acceleration in the negative or down of 9.8 meters per second. If you're sitting in this car, you're actually going to feel more acceleration than you would falling off a cliff as you accelerate. And so I don't know what that's like, but I bet it feels really, really cool. And so I hope that's helpful.